स्लाइड चेंज करनी पड़ेगी then.
Start.
Hello teachers. So our topic is SWIN VQA, in which we are using VQ as a transformer framework for medical visual question answering. Next. So what is VQA? VQ is a basic visual question answering system through which we can extract insights from an image and answer questions based on that image. So right now we are using VQ on a medical data set. So we extract insights from medical images which are very complex. We diagnose it and interpret through the targeted thing or something. And we have introduced SWIN VQ by combining SWIN into VQ. So why would somebody use this? So it can be for preliminary symptom clarification. So if you have a report of your particular organ like lungs or pancreas, and you can give the scan to our model and ask that what can is there anything wrong with the scan or no, and you can it can be a very basic question answering system. Second, next. Second can be for basic purpose like education and empowerment, where you have a scan. Again, you have a scan of your lungs or something, and you don't know what the scan is telling you, and you have no information what is wrong with the scan. So, for just for educational purposes and personal knowledge of what is wrong with your organ, you can give the scan to our model and get to know about any abnormality if there is. Next. And third can be the second opinion triage. So if you have already met a doctor or you're going to meet a doctor, you can give the scan to our model and get the insights of your image, and that through that you can double cross or even question the doctors if he or she is correctly diagnosing you or no. Next.
You.
Yeah, so now I'll walk you through evolution of vision models, the what it was initially and what models were used initially. I'll walk you through. So the VQA system began with usage of CNNs. That is, earlier we had CNNs, then it came to VITs. VITs can handle global context, but computationally expensive and can't capture fine-grained local features. So for high-resolution image, there is some compromise if you are working with VITs. So the new method which we are introducing is SWIN transformers. So with SWIN transformers, we have a hierarchical structure which understands image at different hierarchies, computes local self-attention within windows, and enables cross-window connection. So what we get is global scene as well as detailed object detection. Next. Hello, Jatin.
Yes, yes. Yeah, next. Hello.
Yeah. So the
You can
problem
continue.
definition. Hello. Yeah.
Yeah, continue.
So the problem definition. So currently, what are the problems with the currently existing models? So the first of all, we have scalability constraints. So CNNs obviously can't be scaled because they cannot process. So the serialization is the constraint. With VITs, it's much more we can parallelize the process, but still the complexity, which is O of n square. So let's say you have a very high resolution image. So for that, there is some compromisation. There will be some loss of fine-grained detail. So that's with SWIN VQA, you get O of n complex. The another gap is hierarchical reasoning. So medical diagnostics require understanding of both global as well as the fine-grained details. So with currently existing models, you won't get that, but with SWIN, you can get different hierarchies and different levels. Yeah. Next. Yeah. So yeah, also the reality language misalignment. So clinical questions in clinical domain, we have specialized terminologies that must precisely align with the visual pattern. So if we miss specific term, that won't work. So that is another gap, and practical utility for patients. So uh, such as preliminary symptom clarification, anatomy clarification, and for second opinion purposes. So these are the problems we are trying to solve with our project. Next. So the gaps in existing work. So currently, as I discussed earlier as well, that first of all, it's computational inefficiency. So many state-of-art VQA models, specifically VITs, they are better than the CNs and all. Still the complexity goes quadratic, that is n square. So this is still very much inefficient in terms of power as well as memory. So this restricts the deployment in resource constrained environments such as some mobile devices or embedded systems where low latency responses are essential. The other gap is insufficient spatial and contextual understanding. So the current models lack robust mechanisms to explicitly reason about spatial relationships within the image, such as the relative positioning of the objects, or questions like what is on the left of the image. These are the challenges due to absence of effective spatial reasoning. Next. Also, ineffective multi-scale feature representation. So most of the VQA models which are currently there, they do not incorporate multi-scale representations, which are necessary to capture relationships between objects, attributes, and scene elements. Also, the lack of hierarchical representation. Existing VQA systems often they are struggling to process and integrate the visual information in multiple hierarchies or at different levels. So this limitation impairs the ability to simultaneously capture fine-grained details such as object textures or textual elements and broader scene elements such as overall layout or context. Next.
Okay, I'd like to explain you the model design for our framework. So the model initially consists of a pair of two other models. One is the vision model, which is a SWIN transformer. Then other is a language model. Here we are using BERT. So the user inputs an image. The image is converted into its visual features using SWIN transformer, and the text also has its embeddings through the bot tokenizer. These visual features and text embeddings are then concatenated into an input sequence. This input sequence contains the segment embeddings as well as the positional embeddings, and all these inputs and embeddings together make the augmented embeddings. The segment embeddings basically classify the image embeddings and the text embeddings separately, and the positional embeddings are basically signify the position of each token in the uh, feature representation itself. Then these augmented embeddings are transferred to the transformer block. The transformer block here calculates the cross model attention through all these embeddings, and eventually we get our contextualized embeddings, which have the meaning of the image as well as the text associated with it. Then these contextualized embeddings are given to the answer generation block. Answer generation block typically used by other models is the answer generation method typically used by other models is greedy search, but here we are implementing beam search. What beam search essentially does is it gets you various options of next token, and through that various options calculates the best possible score for each of the option and subsequently calculates the score for the next tokens as well as, and these scores are then normalized, and the sequence with the highest normalized score is chosen. Data description. So here we are using a VQA RAD dataset. RAD basically signifies radiology. It contains image, question, answer, and the question can be closed-ended or open-ended. So closed-ended basically means yes or no. Another data set that we are using for our model to be trained is the Slake data set. Slake data set contains the image, ID, and the modality type. Modality is basically whatever it can be, like CT, MRI. See, the question answer pair for visual question answering, of course, the question type. So, like what kind of question it is, and which it is categorized through different medical queries, and semantic graph structure knowledge representation for enhanced learning. So this is a knowledge representation of the question and the answers, which gives us a better understanding of how the image is related with the question and then the answer. So results and interpretation. Here we are testing basically two hypotheses. One is the answer generation quality hypothesis, and then the other is the computational efficiency hypothesis. I'd like to go through the answer generation quality hypothesis first. The null hypothesis for this is beam search with beam width k is equals to 5 does not significantly improve answer quality compared to query search, which is essentially k is 1, maintaining similar blue scores. Alternative hypothesis is implementing beam search with beam k width is equals to 5 significantly improves text generation quality by achieving at least 15% higher blue scores compared to 3D search. And as you can see, our experimentation gives us really high results, which surpasses our alternative hypothesis, which is 15%, and it actually gives us more than 15% of better results. So we can say that our alternative hypothesis is accepted. Yeah,
Next, the next hypothesis focuses on reducing complexity. So right now the latest model that we have is vision transformers. And let's have a brief of how the algorithm looks like. Uh, Looking at the top right corner, we can see that first of all, the vision transformers divide the image into multiple patches, let's say 1,000 patches, and then we create embeddings of each of those patches. And when we compute self-attention, each of that embedding is multiplied by all of the embeddings. So 1,000 into 1,000 becomes 1 billion. So the complexity of VIT is n square. And when we scale the problem to 4K images, the complexity is exponentially increased, which is not efficient. Hence comes SWIN transformers. Looking at the bottom right corner, we can see that it also divides the image into multiple patches, but then it groups the images into windows, or groups the patches into windows. So let's say if we have 1,000 patches, we have groups of 7 by 7 windows. So now the self attention will be calculated only with that pixels or the patches of those windows. So it will be 1,000 into 49 instead of being 1,000 into 1,000 now. And 49 being 7 by 7 is a constant. We can keep the window such as 5 by 5, 7 by 7, whatever it suits. But by empirical study, we have found that 7 by 7 is suitable. So here we reduce the complexity as 1,000 into k, which is n. So the complexity is reduced from n squared to n. On the bottom left corner, we can see a table where we have three parameters through which we evaluate all of the algorithms that we have currently. So let's say we take a 512 by 512 image. The floating operation per second is significantly reduced of SWIN. And also we can see the memory and at the same time the inference time is significantly or exponentially lower of SWIN compared to the best performing transformer for now is VIT. Hence we can comfortably reject the null hypothesis that reducing complexity is not possible, and we can accept the alternate hypothesis that yeah, when we apply the concept of shifted window partitioning, we can reduce the complexity exponentially.
Yeah, so as you can see, this is how our model works. So we basically give an image, and since we are like make experimenting this on Kaggle itself, so we are giving the part to our image, and the subsequent image is here, and you can just ask a question, what is this image of? And then you can get an answer. The CT scan show a large irregular heterogeneous mass in the upper right quadrant. S- yeah, and there are more such test cases as well. I can show you. Here, this is a scan of lungs. Yeah. So in the conclusion, we would just like to say that uh, we have formed successfully shown that SWIN transformer can outperform the regular vision transformers and in the areas of hierarchical image processing and also for precise answer generation in the NLP model area where where earlier 3D search was implemented, but we implemented beam search over here. And a future scope would be enhancing the knowledge framework more, so getting more data on medical use cases and other scans as well, and limited interpretability. So these answers are basically less interpretable by regular users because there are certain terms which cannot be understood by us. But so these users would have to go to the internet and then ask those similar questions again. But it can be significantly reduced, and also it is also acts as a black box model. So we don't know how much to trust it or not. Yeah, thank you.
Thank you.
Yeah, thank you.
Hello.